Last but not least comes our change from trying to find the exact nearest neighbor to just finding a good nearest neighbor. If we switch from finding the best recommendation to just finding a good enough recommendation, we can make our algorithm even faster. So in our process of finding the nearest neighbor, we started by working with a query point, going to the bin that it resides in, and finding the nearest neighbor so far from within that bin. We then created this distance r between the query point and the nearest neighbor so far, and we only searched within bins that were within that radius of our query point. We notice here that our distance to our nearest neighbor so far, labeled as r, our distance to our actual nearest neighbor is closer, but not orders of magnitudes closer. So for example, what if I said it's really not worth the cost of doing the search if all I'm going to get is marginal savings? I'm really only interested in doing a search for something better if it's orders of magnitude better, way better than the nearest neighbor that I have now. Only if I can gain great savings am I willing to go through the process of searching. So for example, in the visual that we have over here, I've identified this nearest neighbor r. Perhaps I'm only interested in finding a neighbor that's nearer if it's something like at least twice as good as the neighbor that I have right now. And by twice as good, I mean half the distance. From here, instead of using this circle that's purple in the image of radius r away from our query point, let's instead search within a radius of r over 2. Now, will I be missing neighbors that might be a little bit closer? Yes, I can see them all lying right over here. All of these neighbors would be closer to our query point than our nearest neighbor so far. However, they're not orders of magnitude better. In fact, this point and this point are pretty much equidistant from our query point. And so in this sense, if we were using finding a good nearest neighbor, but not necessarily the best nearest neighbor, we would never search within this bin, and we would never consider any of these particular points. So it gives us that computational savings to find a good nearest neighbor, and we aren't interested in replacing that nearest neighbor unless the next nearest neighbor is orders of magnitude better. So this will be the approximation algorithm that we use, very similar to our original KD tree, but taking r and replacing it with something like r over 2 for approximate nearest neighbor searches.